Okay, so now for the coup de grace. We are now looking at the voltage drop across the current viewing resistor of Tar Baby's circuit on the B channel of the probe. And the A channel of the probe, of the oscilloscope, sorry, is looking at the battery voltage across the battery terminals where they connect to the board. So going to the circuit diagram, we're looking with the B channel of the scope, we're looking at this point right here across the current viewing shunt. The ground lead of the probe is connected to the common channel ground, common circuit ground, and the positive tip lead of the probe is connected here. So if current is flowing in the conventional direction, positive to negative, thanks to Ben Franklin, the tip of the probe will be more positive than the ground lead of the probe. So a positive voltage here will indicate that we have current flowing in this direction. If we get a negative voltage here, if this lead is more negative than the reference, that would mean that the current is flowing in the backwards direction, or anti-conventional direction. Okay, so we have a 0.25 ohm current viewing resistor. So the voltage that we measure here will be divided by the value of that resistor to give us the current in amps through that shunt. And we're also looking with the other channel of the scope, we're looking at this point here. Again, the reference lead, the negative is here and the positive is here. So we're monitoring the same two channels that the nerds use to multiply to get their instantaneous current or instantaneous power trace. Okay. So right now I've got the bias supply turned way down, so the system is not oscillating. Here's where the baselines are. The B channel baseline, they're both off right now, and the B channel baseline is, I want to set it right exactly at the center radical division right there. And the A channel baseline is set right there on that one. Okay. So A channel across the battery connection will be at 50 volts per division. The B channel across the current viewing shunt is at 0.1, or since we have the 10x probe, it will be 1 volt per division. How convenient. Okay, so now I'm going to crank up the voltage on the bias supply. Alright. Oh, wait, first let's turn the channels on. Okay, so click, click. So the B channel didn't move because there's no current flowing through the system. The A channel jumped up. The A channel is the battery voltage, right? So it jumped up to the battery voltage, which is still over 12 volts each. Okay. So now I'm going to crank in some bias current using the supply. Okay, here we go. More. And you see the oscillations, right? And let's just go ahead and crank it on up to a nice robust figure. We'll give it 10 volts or so. All right, and that'll give us 175 milliamps on the Hickok, 180 to 200 milliamps going through the system. That's enough to produce load heating. Okay, the load's going up. It's actually only about 25 ambient here. And the nice big robust oscillations. And let's go ahead and crank the time base down so we can see what those do look like. If I can get the scope to trigger, there we are. Okay, so now remember where the zero lines are. For the B channel, oh wait a minute, let me go one more here. There we go, okay. Alright, for the B channel, right, oops, anyhow, the zero marker for the B channel is right across there, right across the center, right? So this is across the current viewing shunt. So the peak voltage in the conventional direction is about 1.1 volts, and by Ohm's law, let's see, we get the voltage drop 1.1 divided by 0.25, the value of the current viewing shunt. That gives us a peak current value of about 4.4 amps. So trigger 4.4 amps is the peak current in the positive direction. Now then, going in the negative direction, we have 2 full divisions there. And so 2 full divisions, that's 8 amps at 0.25 current viewing, 0.25 ohms for the current viewing shunt. Okay, so the peak current in one direction, in the so-called anti-conventional direction, is higher than the peak current in the normal positive direction. But look at the areas here. So compare this area right here with this area right here, and they're actually just about equal. This area right here is almost exactly like 1 square division, and then so is this. If you shaved off that and stuffed it in the sides, you would have just about 1 square division for both of these areas, positive and negative going current flow. Okay, now this is the battery trace up here, and the baseline for the battery trace is running right along here, right? So this is AC. It's oscillating back and forth across the zero baseline, positive flow, negative flow. But this is just a ripple sitting on top of a DC offset. This is not truly AC, right? Because the polarity doesn't reverse. The direction of this current does reverse, but this doesn't. All right, so notice the phase relationship. They're just exactly the phase relationship that, if I can get it to trigger stably, it's just exactly the phase relationship that Ainsley talks about in the paper. They're 180 degrees out of phase, right, as they ought to be. And then if you were to actually take this positive going area and multiply it by this, by the instantaneous voltages all along the way, would you, the question is then, would you in fact see a greater product of, say, this area times this area than you would of this area times this area, right? Because remember where this is oscillating around the battery voltage, which is this radical marker or just below it right here at 50 volts, right? So you've got an area above that 50 volts and an area below that 50 volts. So you would, since the sum of the integrals is equal to the integrals of the sums, you can take this area and multiply it by this area, and effectively that's the same as doing the multiplication first and then integrating, okay? So the question then is this area times this area greater than this area times this area? Okay, so we'll leave that as an exercise for later. Thanks for watching.